When we apply a step input to a stable system, the output rises and eventually settles at a final value. That final value, y of infinity, is what we want to find. Today we will use the final value theorem to compute it directly from the transfer function, without solving any differential equations. Here is our problem. We are given two transfer functions. g1 of s equals 3 times s plus 4 divided by 2s squared plus 4s plus 1. g2 of s equals 3 times s plus 4 divided by 2s squared plus 4s minus 1. Notice that the only difference is the sign of the last term in the denominator, plus 1 versus minus 1. For both systems, a unit step input is applied. We need to find the limit of y of t as t goes to infinity. The final value theorem states that the limit of y of t as t goes to infinity equals the limit of s times y of s as s goes to 0. Why does this work? Recall that the Laplace transform of a derivative is s times y of s minus the initial value y of 0. If y of t approaches a steady value, its derivative approaches 0. Taking s to 0 in the Laplace domain corresponds to taking t to infinity in the time domain. That is the intuition behind the theorem. For a unit step input, u of s equals 1 over s and y of s equals g of s times 1 over s. So s times y of s simplifies to g of s. Therefore, y of infinity equals g of 0. But there is a critical condition. All poles of s times y of s must lie in the open left half plane, otherwise the limit does not exist. In practice, this means the transfer function g of s must be stable. If the system has a pole with positive real part, the output contains a growing exponential term and does not approach a finite value. The final value theorem gives a number, but that number is wrong. So the plan is, first check stability, then, if stable, compute g of 0. Never skip the stability check. Check stability of g1. The denominator is 2s squared plus 4s plus 1. For a second-order polynomial, there is a quick rule. If all three coefficients have the same sign, the system is stable. Here all three are positive, so g1 is stable by inspection. This shortcut comes from the Routh-Hurwitz criterion applied to a second-order polynomial. The first column of the Routh array is just the three coefficients themselves, so no sign change means no right half-plane pole. Let us verify with the quadratic formula for certainty. The roots are s equals -4 plus or minus the square root of 16 minus 8, all divided by 4. That is -4 plus or minus the square root of 8 divided by 4. Simplifying, s equals -1 plus or minus the square root of 2 divided by 2. Numerically, the roots are approximately -0.29 and -1.71. Both have negative real parts, so both are in the left half plane. Stability is confirmed. FVT can be safely applied. Now apply the final value theorem to g1. Since g1 is stable, the theorem holds. Y of infinity equals g1 of 0. Plug in s equals 0. The numerator becomes 3 times 0 plus 4, which is 3 times 4, which is 12. The denominator becomes 2 times 0 squared plus 4 times 0 plus 1, which reduces to just 1. So y of infinity equals 12 divided by 1, which equals 12. That is our answer for g1. The step response of g1 starts at 0, rises, possibly overshoots, and eventually settles to the horizontal line at y equals 12 as time grows large. The exact shape depends on damping, but the steady-state value is unambiguous, 12. Check stability of g2. The denominator is 2s squared plus 4s minus 1. Notice that the constant term is now negative. This is an immediate red flag. For a second-order polynomial with leading coefficient positive, the product of the roots equals the constant term divided by the leading coefficient. Here the product is -1/2, a negative number. Negative product means one root positive, one root negative, and a positive root is a pole in the right half plane, which makes the system unstable. Let us compute the roots explicitly. Using the quadratic formula, s equals -4 plus or minus the square root of 16 plus 8, all divided by 4. That is -4 plus or minus the square root of 24 divided by 4. Numerically, s is approximately 0.22 and -2.22. The root at positive 0.22 is in the right half plane, so G2 is unstable. The final value theorem does not apply. Since G2 is unstable, the final value theorem does not apply. You might be tempted to just plug in s equals 0 anyway. G2 of 0 equals 12 divided by -1 equals -12. But this number is completely meaningless for our problem. Let us see why by thinking about what y of t actually looks like. When we take the inverse Laplace transform of y of s, which is g2 of s times 1 over s, we do partial fraction expansion and end up with terms like 1 over s minus 0.22, and 1 over s plus 2.22. Each term in the s domain corresponds to a time function. The 1 over s term gives a constant. The 1 over s plus 2.22 term gives a decaying exponential. But the 1 over s minus 0.22 term gives e to the positive 0.22t, which grows without bound as t increases. This growing exponential dominates the response. The output diverges. The limit of y of t as t goes to infinity does not exist. Lesson learned. Always verify stability before applying the final value theorem. Without stability, the theorem gives you a finite number that has absolutely nothing to do with the true long-term behavior. Let us summarize. The final value theorem gives y of infinity equal to g of 0 for a step input, but only when g of s is stable. For g1, all denominator coefficients are positive, so g1 is stable. Y of infinity equals g1 of 0 equals 12. For g2, the constant term is negative, so one root is in the right half plane, g2 is unstable. The output diverges, the limit does not exist. Always check stability first, then apply the theorem.